All right, this is the fourth FRQ from the 2016 BC exam. So they're asking us first to find the second derivative. This is in terms of x and y, so we're using implicit differentiation here. So I've got dy dx equals x squared minus 1/2 y. And then I'm going to say the second derivative is 2x minus 1/2, and then the derivative of y is dy dx. So that means that what I have for my second derivative is 2x minus 1/2 times x squared minus 1/2 y. And you can leave it like that with parentheses, or you can distribute. It really doesn't matter. So both of those answers should be good, get you full credit. All right, part B. I'm sorry if you can hear background noise. My kitten is going nuts right now because he just took a nap, so he has energy. All right, part B. Let y equals f of x be the particular solution, and then we want to determine if the graph has a maximum, minimum, or neither. So I decided to kind of work with the information I had to figure this out. So the first thing I wanted to verify, which you probably don't have to do, but I'm going to go ahead and do it anyway. First thing I'm going to do is just verify that that point is in fact a critical point. Or that the x value of -2 is a critical number, which means that it makes the first derivative equal 0. So since they gave it to you, you probably don't have to do that, but I figured I'd do it anyway. So -2 squared is 4. We've got 4 minus 4 is 0. So we have checked, yes, it is a critical number. Now, the other part of this, we typically used only the first derivative, and then we would make a sign chart, figure out our pluses and minuses. But and you can still do that. If you want to use the first derivative to figure out the problem, you can. But the second derivative test is actually one that you can use. So you can take the concavity and you can use that to figure out if the graph is concave up, that means it has a minimum there. If it's concave down, that means it has a maximum there. So I'm just going to take that second derivative since we just found it and do the problem that way. So I've got -4 minus 4 plus 2. So -4 minus 1/2 of 4. So -4 minus 2 plus 2, -4. So I'm going to say that we have a relative max at the point -2, 8, because the first derivative equals 0, and the second derivative is less than 0, which means that the graph is concave down. So since the graph is concave down, that means you have a relative maximum there. Okay, and again, so I use the second derivative. You don't have to do it that way. I know that we typically didn't do it that way just because we, why go through the work of finding the second derivative typically? But in this case, since I already have it, I just decided to use it. Okay, next question says to find the limit, and we're using that, we're finding, here it is, the limit of this, and we're using that g of -1 is 2. So I've got the limit as x approaches -1 of g of x minus 2 over 3 times x plus 1 squared. So anytime I think that this has the potential to be a L'Hopital problem, then I'm going to go ahead and make sure my notation is good. So I'm going to say the limit as x approaches -1 of g of x minus 2. And on the front side of the page, I learned that the function evaluated at -1 is 2. So that gives me 2 minus 2, which is 0. And then the limit as x approaches -1 of 3 times x plus 1 squared is going to be 0 because you're plugging in a -1 here. And so because of that, we're going to use L'Hopital's. All right, and so that means that next I have the limit as x approaches -1 of g prime of x divided by 6 times x plus 1 to the first power times 1. All right, and then let me go back over here. So it says that g of x is the solution to the given differential equation. That means that if we look up here, that this is the differential equation that we're using. So for me to figure out what g prime at -1 is, I have to take the differential equation and plug in -1 for x and plug in 2 for y. So I'm going to go ahead over here and do dy dx evaluated at -1, 2 is going to be -1 squared minus 1/2 times 2. And that's 1 minus 1, which is 0. So again, I'm expecting it to be L'Hopital's, so I'm going to use the proper notation. So the derivative, or the evaluation of the top is 0. The limit of the top is 0. The limit of the bottom is 0. We're going to use L'Hopital's again. So now I've got the limit as x approaches -1 of g double prime of x divided by, on the bottom I can think of that as like 6x plus 6, and so the derivative of that is just 6. And so now what I need to do is take the second derivative and evaluate that at the same point. And so the second derivative is going to be 2 times x minus 1/2 times x squared plus 1/4 times y. And that's -2 minus 1/2 plus 1/2. So that's just -2. So I end up with -2 over 6. And so the limit is -1/3. All right. And then for part D, it says that we're using Euler's method. So we're using the initial value 0, 2. We're using that differential equation. We're trying to find h of 1 with 2 steps. All right, so for Euler's method, I have the old x, I have the old y, then I have the change in x, then I have the slope, which is dy dx is x squared minus 1/2 y. Then I do change in x times the slope plus the old y, and then that gives me the new y. And you can definitely kind of condense this table down. I have never done that because this is just the easiest for me to remember. So I always do it this way. So we're starting off with 0, 2. We have 2 steps. We're ending up with an x value of 1. So that makes this 1/2, 1/2, 1/2. Okay. So dy dx is going to be 0 squared minus 1/2 times 2. And so that is -1. So I've got 1/2 times -1 plus the old y value. So -1/2 plus 2 is 3/2. Okay, so my new y value is 3/2. Okay, so I've got x minus 1/2 of y. So that's 1/4 minus 3/4, which is -2/4. Okay, so I have the change in x times the slope. So -2/4 is -1/2 plus the old y value. So I've got -1/4 plus 6/4. Negative 1/4 plus 6/4. So in my head, I'm thinking 3/2 is really 6/4, which gives me 5/4. And so I want to phrase my answer the same way. Approximate h of 1. H of 1 is approximately 5/4 using Euler's method.